Hello everyone, my name is Amal Al-Rumi and today I'm going to be presenting my parametric modeling final project, the Golden Sands Lake Grand Theatre. A brief overview of the project: it was designed by CCTN Designs, with the lead architect being Yofen Wang. It's located in the Guangtan district in Hangzhou, China, and completed construction in 2023. A breakdown of the building's main elements: we have the core volumes, the roof and facade envelope, the window openings, and the triangular tessellation pattern. To achieve this pattern, we have to start with connecting the core volumes and building outwards. As you can see from the top view, this is how it was done in the building. Moving on to the definition. I first started off by creating the curves for the two central shapes, moving them upwards and offsetting them. Then, in order to create a similar angle to the building itself, I used a point-on curve and closest points in order to create an interpolated curve that could be adjusted. Now that we have the top and bottom for each of the central curves, we offset them, divide them, then using 4-point surface to generate the surfaces that will later be extruded in order to create the panels. In order for the offsetted shape to match the building more accurately, we have the divide curve component along with a graph mapper connected to a NURBS curve so that the offsetted shape is parametric. In order to merge the two shapes, we create a line between the centroids, and using the rotate battery, we get the intersecting points. Then using these intersecting points, we cut the curves and blend them. In order to achieve these openings, we first divide the curve, then by using closest point and moving them in the z direction, we can determine where the openings are, how high they are, and how thick. As previously mentioned, the layout of the roof follows a figure 8 shape with this connecting panel in the middle. Using a mesh UV panel will create some irregularities. In order to achieve this, we need to match the internal and external control points, as well as match the patch that will be in the center. Using surface closest point and the existing shapes, we create the refined middle patch. After we have the central points, we plug them into a solver in order to create the correct mesh that allows for the connection. Using Weaver-Bird's naked boundary, we extract the central lines that have the correct number of control points, then plug them into a parameter loft mesh and Weaver-Bird's join mesh and weld. As you can see, this follows the shape that's in the top view. Since the roof of the building isn't flat, we take this face of the boundary box battery from the top mesh and plug it into a graph mapper, which then creates a surface that we can project the points onto. In order to weld the two meshes, we need to unify the mesh edges. We do this by taking the already correct roof, then matching the edges to the second mesh. Then we further subdivide that mesh and weld. In order to achieve the final shape, we take the mesh and, using the pressure goal in the negative direction as we want it to expand, we plug it into a bouncy solver to achieve the final shape. And the more in the negative direction you go, the bigger it expands. A previous failed attempt of this was done using the same goals except for the vertex load, where instead of inflating outwards, it pushed it inward. Finally, we take Weaver-Bird split polygon subdivision along with triangulate in order to achieve the correct pattern. But as you can see, it isn't all unified. So we take a control point that uses distance in order to determine which places are open and which places are closed. For the windows and railings, we take the bottom curve and pipe it to create the outline for the openings. Loft the top and bottom surface for the window and pipe for the mullions.